Next, I'm going to show you how to calculate the power of a one proportion z-test. This builds on what you know about normal distributions from Unit 2 and what you know about one proportion z-tests. And I'll demonstrate with a few examples. It's a two-step process. Basically, if you want to find this power, the first thing you have to do is to use the null hypothesis, the alternative, your alpha level, and your sample size to find the values of p hat that would lead you to reject the null hypothesis. And then once you've found those values of p hat, you want to find the probability of getting one of those values of p hat if a specific alternative PA is true. Now, you might recall from the previous video this diagram, and this shows the state of the world according to the false null hypothesis and the true alternative. We want to find this area basically, which is the probability that we're going to be able to reject the null hypothesis. Up here, there's some values of p hat that would cause us to reject the null. Anything is to the right of p hat star. And then down here, we're going to use this as our mean and the standard deviation for this distribution to standardize and figure out the probability that the p hat that we get is greater than this p hat star. Okay, so that's what we're going to do. I'll show you with a few examples. Example 1, we're going to assume that P naught is 0.4 and the null is P is 0.4 and the alternative is P is greater than 0.4. So this will be a one-tailed test on the right. We're going to use an alpha level of 0.5 and a sample size of 100. And we're going to assume that the true alternative value is 0.44 rather, for the true alternative. Okay, now here's the world according to the null hypothesis. We want to find the probability. Actually, what we're looking for here is values of p hat that are over here to the right of this value right here, that are in the upper top 5% of the whole distribution of all the p hats. So basically, we want to find the 95th percentile of this distribution and then figure out the probability of getting a value of p hat that is bigger than that 95th percentile. Now this is a normal distribution. If we were to standardize, the z-score that we would get that corresponds to the 95th percentile is 1.6449. I can get that from inverse norm 0.95 on my calculator, and I can find that. And anytime I run this test, if I get a z-statistic that's bigger than this, I would reject the null hypothesis, and everything would be good. Okay? Now, if we want to figure out what p hat corresponds to this value of z, we're going to have to do a little bit of unstandardizing. We're going to reject the null hypothesis if z is greater than 1.6449, and z has this formula in terms of p hat, p naught, and n, and we're going to plug in p naught from the null hypothesis here, and 1 minus p naught from the null hypothesis there, and the sample size there. We're going to simplify that down, and we get p hat minus 0.4 divided by 0.0490, and if that's greater than 1.6449, then we would reject. Well, we're going to solve this little inequality for p hat, and we're going to reject if we get a p hat that is greater than 0.4806. Okay? Now we want to figure out the probability of getting a p hat bigger than that if the alternative is true, that the true population proportion is 0.44. And so this is what we want to do. The power is the probability of getting a p hat that's bigger than that. So it's out here in the rejection region there where we're going to reject the null. And we're going to use this to find this probability. Now to find this probability, it's basically a standard normal calculation that we have to do. We're going to use this for the values of p naught or p in our standardization process. So when we standardize, we subtract the mean of the p hats divided by the standard deviation of the p hats. Well, the mean is this, 0.44. Standard deviation is the square root of 0.44 times 1 minus that, 0.56, divided by 100. And then when we simplify that down, we're going to get a z-score of 0.8179. And if we get a z-score greater than that in the alternative distribution, we would reject, and that's going to happen about 20.67% of the time. So that's not a very large power, but that is the power. The beta, the probability of a type 2 error is 1 minus that, be 0.7933. That's very large. That means almost 80% of the time you're going to fail to reject the null hypothesis when it is in fact false. Okay, so we need to, hopefully do better than that. Now, what we're going to do next is we're going to look at a second example. It builds on the first one. We're going to assume all the same information that we had before, except we're going to change the effect size. So it's the alternative that we think is true is no longer 0.44, but is now 0.5. So the difference between these is now 0.1. That's a pretty large effect size. It was 0.04 before. So we want to see what happens when we do that. Okay? Well, as we did in the previous example, we reject H0 if p hat is greater than 0.4806. Nothing has changed in that calculation. We used the same alpha, the same p0, the same n. So nothing has changed. So it's the same value of p hat. And the power is the probability of getting those kinds of values of p hat if the true alternative is 0.5. And you standardize using that true alternative. So we subtract the mean divided by the standard deviation on both sides of that inequality, and then we get a z that's negative 0.388. The probability that we get a z greater than that is about 0.6510. And that's much bigger. The power before was about 21%. This is over 65%. So it's a much higher power. And that generally, is true. Whenever you increase the effect size, that increases the power of the test. It also reduces the probability of a type 2 error.